All right. So I'm just going to start by, hi. I'm going to start by, I hope you're fine. I'm going to start by asking if the sound is okay. I'm not using my usual setup. It's one of those rigged. I had to rig it up quickly here. So it's those funny headsets where, anyways, I hope you can hear me though. I hope you can hear me, and I hope you can see my slides.
Yes, sir. Yes.
Okay. So I don't know if you guys had a chance to think about what we discussed yesterday, I believe, in the morning, when we started looking at. Well, we looked at we wrapped up by looking at so-called video encoding, really, and we talked about a bunch of things, things like resolution and the implications of using certain types of resolutions, and in fact, at some stage, I guess before we part ways, we had a simple walkthrough where we were highlighting exactly how we could identify the different frames associated with a particular video. So what we did, right, was we got a video from Lighton's YouTube channel, right? This video here, which you can access by just going to this link here, https blah blah. And then we downloaded the 720p version from YouTube, because remember we mentioned that in passing that what YouTube does when you upload a video to their platform, especially if it's a high quality video, it's a high definition video, 4K, as is the example for this video. It was uploaded in 4K. What YouTube does is they transcode the video into different formats, right? These are the things that you tend to see when you go on YouTube and you click on that cog, yeah? You will see the different resolutions that you can download from YouTube, right? Now, if you upload a low quality video, obviously there's no way in which YouTube will transcode it to 4K. if you take a video using like an old phone, and then the quality is, let's say, the resolution is 320p, for instance. And I'm looking for a low quality, let's say movie TV. I know movie TV probably don't, movie TV. I don't think those people, TV, no, not TW. I don't think those people upload high quality video footage. Let's look at what they did today. If you upload, what we're saying is if you upload a low quality video, it will only be dumbed down from that particular resolution, the original resolution. So if you upload a 720, you only scale down, right? You don't go up. Of course, I mean, there are people that are probably able to reconstruct lower resolution videos to sort of like come up with higher quality videos. But let's look at, no, I want to look at, we don't want controversial here, but let's look at why are we even struggling to pick up, let's look at this with the tractor anyway. So if we pick up this thing here, you notice that if I click on this cog, I suspect, there's an advert, I suspect Movie TV does not upload high quality videos, right? I don't know what sort of equipment they use, but you notice if I click on this cog, there's no 4K anywhere here, right? It's just your 1080p, right? Which is okay, I guess. It's standard. I mean, it's expected. Your average smartphone will probably, at the minimum these days, will probably record videos in 1080p. And in fact, that's the default. Why do you think the default for your average mobile phone is 1080? Why is it that even if it's capable of recording 4K, why is 4K not used? Any thoughts?
Sir, I think it's because they're looking at the size of the video, if it was going, or video when it was going to be recorded in 4K.
Yeah, I mean, that's likely the reason, right? That's a good reason, actually. And think about this for a second. If you look at our example from yesterday, where you have a video that is 1 minute and 39 seconds in size, right? But it occupies almost 200 megabytes of space. Think of how much space a typical video in 4K would be able to occupy. You must think about these things, right? Think about this, and you can actually derive some of these things and try and make sense out of what's happening here. right? So assuming that not assuming actually, your average movie, for instance, will be maybe 1.5 hours in duration, right? 1.5 hours is a total of 1.5 hours is 60 minutes plus 30 minutes, which is 90 minutes, right? If we convert this into seconds here, it's just 5,400 seconds, right? So here's the thing. If we are saying a 1 minute, this segment here, this in 4K, this video, which is 1 minute and 39 seconds, effectively, 60 plus 39. If 99 seconds gives you, it's direct proportion now, I suppose. If 99 seconds gives you 200 megabytes, what will 5,400 seconds give you? Right? You have to think about this for a second, right? This is one of the reasons why, as Lando rightly pointed out, it's one of the reasons why by default this is switched off. You have to explicitly, that's a lot actually. If we divide by 1024 here, you notice that we have, it's almost a terabyte.
So,
right? Notice it's 1054 GB. Yes, sir.
so this means that for as long as we have the time and the size, we can still calculate the throughput even in data encoding, right?
I don't understand the question.
Like, since topics in ICT are connected, it means even in data encoding, we can be asked to calculate the throughput, right? We've got the size, the file size, we've got the time.
Yeah,
Does that
it
mean?
depends. I mean, it's I don't see how there's no connection between throughput and encoding here.
No, I'm just looking at the things we are looking at, size and the time taken. Looking at which one you'd prefer, whether downloading a 4K video or 1020p video, and then I'm just looking at the things, the contents that will be given. So I'm just trying to find out whether we can still calculate throughput through the things we've been given so far, time and the size of the file.
Yeah, but I mean, throughput is derived from a quantity and time. So it doesn't matter in what context you're viewing it. I mean, it could be speed, it could be anything. So yes, you can. If you're given a quantity and the duration, you can compute the throughput. So yes, you can. Indeed, you can. Indeed, you can. All right. So we spoke about video resolutions here, and we looked at this example, and we ended at the stage where we're trying to talk about these different aspects associated with how you get to decide on what sort of resolution you might be interested in consuming as an end user, right? So you take into account things like cost, the amount of time it's going to take for you to render the video. The last thing you want is to compromise your overall user experience when you're watching a YouTube video. I don't know if you've experienced this, but you're watching a video and then you have that spinner that comes up, right? Because YouTube in the background is trying to buffer the content. Your speed is not fast enough such that the content coming on the other side is able to reach you in good time. So what does YouTube do, right? The way it's implemented is as a heuristic behind the scenes that buffers the content, right? So if you're trying to avoid that, then you're better off getting a lower resolution, right? And take into account things like the device you're using to consume this, right? So if you're watching this clip here on a computer in 240p, it might look horrible, right? It will look horrible actually. But when you watch it on a much smaller size device, like a mobile phone, maybe it won't be as bad, right? It's like those billboards that you see somewhere near Mandahi or something. Because they're on a large screen, they appear as though they are pixelated or something, but in actual fact, if you were to view them on a much smaller screen, I mean, your perception of how it looks like wouldn't really be that bad. But anyways, so the question then is how exactly do we get to encode sound, right? So we've looked at how text is encoded, how color is encoded, how images are encoded. Effectively, image encoding makes use of color encoding implicitly, and indeed how video is encoded, right? Which is nothing more than a combination of sound and and images presented to you in rapid succession. And so the question is, how exactly is sound encoded? Well, it turns out it's not that hard, really. The thing to think about here when you're looking at sound is to try and think about what happens when you want to convert your sound wave, right? So when you're speaking, when somebody's speaking to you, the sound that is coming out of somebody's mouth can be represented using a sound wave, right? And this is basic physics that you looked at, I think, in grade, I don't know if it's grade 8 or something, right? So sound is nothing more than a series of vibrations here in the air, right? And because there's a consistent pattern, you can, and computers are good at pattern recognition, you can easily provide a mapping from this sound wave to a representation of ones and zeros. And so this is the essence, this is what we're going to talk about, right? All right, so you have your so-called sound wave, right? And it turns out that you can pretty much view this sound wave from a perspective of your so-called XY axis, right? The thing to remember about sound here is that it has some sort of temporal effect here. It's continuous. When someone is talking to you, what is coming, the vibrations are relative to the duration within which the sound is coming from their mouth, right? So it's a continuous stream of information coming to your end. The reason I'm bringing this up is because if you think about what we are doing with digital computers, the values that we work with are discrete values. We keep saying it's ones and zeros, right? They're discrete, they're not continuous. So that's something else that you need to think about as you are converting your analog sound wave into digital format, right? The fact that you'll have to take care of that temporal effect, right? And it will make sense very, very soon, I assure you, right? So you have your x-axis and your y-axis here. And it turns out that one of the very first things that you do when you're encoding sound, right, into digital form is you have to sample the sound wave, right? So you go through a process where there are 3 phases actually. So there's sampling, there's what they call quantization, and then there's encoding, right? So with sampling, the idea behind sampling is you want to figure out how you can identify discrete values on that sound wave that you're working with, right? So let's just assume somebody's talking to you within a second or something, and you're able to represent that sound wave, you're able to represent that sound using this sort of sound wave. The idea behind sampling is you identify discrete points on this waveform that you're going to eventually use to encode the sound into digital form. Right, so the sampling process will involve you taking the so-called amplitude values here, right, on the y-axis, and then it will be relative to a unit time here, right? So that will be your sample rate essentially, right? I'm wondering if this is making a lot of sense here, but
so
yes, hi.
It's what are the variables we're given here? It's only how do you calculate the amplitude here? The number of photons.
Well, you don't calculate the amplitude. The amplitude is dependent on how exactly you're wanting to represent those discrete values, right? And this is where the idea of bit depth is supposed to come in. I'm wondering why it's here. It's not here. So it turns out that when you're working with sound, you typically have to identify an appropriate bit depth that you're going to be working with, right? So let's say you want to encode the sound using a bit depth of 8. What that means is that the discrete values that you're getting, and in fact this example here is making use of a bit depth of 8 if you think about it, 0 up to 7 here. The values that you're going to be working with are going to be confined within the bit depth that you're working with. Right, so 0 through 8. And in fact, if you again think about this, you realize that the discrete values that you're going to be working with, if they're to be associated to ones and zeros here, they're going to match, they're going to be matched to these real numbers here, these whole numbers from 0 to 7. Right? So 0 through 7. If you're working with a bit depth of, let's say 24, for instance, then you'll be working with values 2 to the power 24, right? So same sort of technique here, right? Right, so something else that you need to take into account here is the sample rate, right? So the frequency within which you're going to be taking note of these values. And so it turns out that I'm trying to see if there's a concept that I'm going to miss out here. Trying to see if there's something that I'm going to miss out here. Probably not. Okay, so you have your sound wave, right? You have an amplitude that you're working with. An amplitude is mapped onto your bit depth, right? Let's assume it's 8 in this case. And then something else that you have at your disposal is the sample rate, right? So how frequently you're going to get the samples that you want to convert to digital form. Remember, at this stage, this waveform that you have is analog, right? The goal is to convert this to digital form. For us to convert it to digital form, we need to identify the minimum and maximum values that we're going to be working with and how frequently we're going to get these values. So in any given second, for instance, how many values do we want to get so that we're able to reconstruct the sound, the analog sound? This is the basis of converting from analog to digital, right? You want to be able to reconstruct what you're encoding into digital form, right? So the way you get these values here is once you identify your sample rate, let's say you decide to say you are going to work with a sample rate of 5, for instance, 5 Hertz. You want to get 5 samples in any given second. And this part here, let's just assume a couple of things here. Let's assume this segment here represents a second, for instance, right? What we are saying is that working with it 1, 2, 3, 4, 5. Well, I guess we can say it goes up to here or something, not up to. I want to make sure this works up to 5, 2 or 5. Let's say this is a second segment. Let's just assume this is a second segment, meaning that we're getting 5 samples in any given second, right? And we're working with a bit depth of 8. So for each 1 second segment, you're going to be getting 5 samples. Now, it's entirely possible, right, that some of the samples will not match directly to, this is so sad, but some of the samples might not match directly to these numbers, these whole numbers that you have, 0, 1, 2, and 3. So part of what you do, right, is you need to round them off to these whole numbers. So if let's say one of the samples that you're getting is in between 5 and 6, what you do is you round it off to the nearest whole number here, right? So that you're able to reconstruct it to something that is as close as possible to the original value associated with the sound wave. Right?
So
that will be your quantization process. And then finally, you encode it into ones and zeros. Yes, sir.
When rounding off to the nearest whole number, do you get the value before or the value after?
No, you get
Like let's say
it's a normal rounding off. You get the number that's closest to the closest whole number or something. So if the amplitude is, let's say 5.7, then that would be 6, right? You're rounding off to the nearest number.
All right.
Yeah. All right. Great. So the rounding off process is what's called quantization. And then after you quantize these values, you realize that you'd have a stream of ones and zeros. So your 0 will be, if you're using a bit depth of 8, your 0 will be represented using 8 zeros, right? And then your 1 will be 7 zeros and the 1 at the end, right? And then what you do when you're encoding this into digital form is you get the continuous stream of ones and zeros that is used to represent the entire sound wave. And then that would be your converted digital form of the analog sound, right? You'd have converted it to digital form. The interesting thing here is that all of this is done by, so the conversion from analog to digital is typically done by what's called, is it an ADC, analog to digital converter, and then the conversion from digital to analog is done by the digital to analog converter, which is the DAC, right? And it makes sense, right? So when I'm using my microphone, there's obviously an analog to digital converter that is going to convert the sound into digital form. That digital form is going to be stored onto my computer, right? Obviously, I'll be able to save, maybe I'll save the sound. If I'm a musician, I'll record a song and then save it onto my computer. If I want to play it back, or if somebody wants to play it back, the reverse has to be done, right? So you're converting the digital form into analog via the speakers, and then someone will be able to play back whatever was recorded. And this makes sense. This explains why, because you are approximating, the conversion from analog to digital is an approximation. Because it's an approximation, this explains why certain sounds that you typically play back is not very clear. For instance, when someone is calling you, have you noticed that the sound is usually not as clear as let's say when you're using a VoIP application like WhatsApp or something? I don't know if you figured that out. It turns out that the bit depth that is used by these mobile service providers is much smaller than the bit depth associated with VoIP applications, than the bit depth that is associated when you're using computer software like Audacity, for instance, right? So key takeaway point is the bit depth that you're using will get to influence how close as possible you're going to get to the sound that you're encoding into digital form. You must try this. If you haven't thought about this, if this is still not making sense, you might try this, right? Try and call someone. I don't know if, have someone call you using MTN or Zamtel. Just pay particular attention to the sound that's going to come your end, and then have them call you via WhatsApp or something, or Google Meet or something. You notice that the quality is different. And this also explains why the quality that you get from music that you download online, for instance, is usually much better, right? Than VoIP calls, than things that you listen to when somebody calls you on the telephone, because the bit depth are slightly different here. So this leads us to our discussion of some factors that will tend to affect the quality of audio that you're encoding into digital format, right? Obviously, sampling rate, how frequently you are getting these samples. If you're getting more samples, the quality is going to be much higher, right? If you get less samples, the quality is going to be much lower. But of course, you're giving up something, right? The more samples you get, the more space the resulting file is going to occupy on disk, right? So there's something to think about here. The bit depth that you're working with also influences the quality. The higher the bit depth, the higher the quality. Yeah, and so applications like Audacity, for instance, will typically allow you to decide what sort of bit depth you're going to be working with. And I can't remember where exactly you get to set this bit depth here, but I guess it should be somewhere. I don't know. I don't know. It should be somewhere here. Is this making sense, right? The idea that you go through three steps, right? When you're converting an analog sound signal into digital format, you first of all have to sample it, right? You go through a process called sampling, where you identify the discrete values, the number of discrete values that you're going to be taking in any given unit time, and that unit time is usually a second, right? Once you identify that, you go through a process called quantization, where you map on these discrete values to the nearest whole numbers associated with the bit depth that you're working with. And then finally, you encode the discrete values in binary form, right? So 7 will have to be encoded into its equivalent binary form using 8-bit representation, obviously. the 6 would have to be encoded in the same way. And then finally, you come up with a stream of 1s and 0s, right? Which is just a concatenation of these discrete values here.
Sir,
Yes, sir.
so when representing -4 on the graph there, since 0 represents the positive and 1 represents the negative, you just start with 0 instead, just to show it's a -2. Since -4 is like the first one there. Yeah, since -4 is like the first one there. If you're about to put this whole thing into binary, does it mean that when you're presenting -4 in binary, you're going to start with 0?
What do you mean starting with 0 when you represent -4?
To show that, oh, sorry, 1, to show that it's a negative number you're representing.
Yeah, well, it depends on the technique that's used. I mean, so if it's 2's complement, then yes, obviously, it will have to be, you'd have to take that into account as well, the negative values.
Right.
Yeah. All right, so what I'm going to do is there's usually an experiment that we normally do, but I don't know, I think we'll skip this. We normally download the national anthem from Wikipedia. I think there's also a site where you can download the high quality national anthem. And then we sort of like modify it so that we have varying, bit rates, bit depth, and then you get to play it back to try and identify the differences in the quality of the sound, right? It's a nice way of, maybe we should do that. But it's a nice way of trying to, let's see if we have this on Moodle. We should have it, if not I'll upload it. It's a nice way of trying to appreciate how quality is affected as you are altering those different factors, and also how things like the file size is going to be affected as well. And these are all important decisions, right? You have to think here, if you're a mobile operator, why do you think MTN would want to use a bit depth of 8 and not a higher quality, or a bit depth that will result in a high quality sound, right? Turns out that you want to make optimum use of bandwidth, right? And one way of making optimum use of bandwidth is to compromise the quality. And I think this should be the ones here. So I will duplicate these and then I'll share them, I guess. It'd be nice. All right, I mean, so just to kind of revisit this conversation again, the idea of how a computer, we've talked about this already, but it needs to sink in, how a computer will know what sort of data it's working with, right? Because remember, all it sees is a continuous stream of 1s and 0s. So how is it going to know that this stream of 1s and 0s is textual content or sound or video or image or it's color, or perhaps it's a combination of all those different things? Well, the software is going to do this. In fact, the computer doesn't care, right? The person who cares what this is a human being, right? So the application software will help the human being try and figure out whether this continuous stream of data is actually textual content, in which case the individual will be able to see, I guess, textual content, right? Alphanumeric characters, assuming it's English here, or assuming you're using an encoding scheme like ASCII. And then if you realize that it's a video file, then obviously you'd have to play back the video using an appropriate piece of software. So, but the key thing here is that the computer will know how to process the data by specifying an appropriate application software or appropriate program instructions that should be used to process these instructions or process the data, right? And remember, again, this ties into the fetch, decode, execute cycle, right? You need instructions and data. The instructions will work on the data. And by the way, this it's difficult to try and consume something that has a combination of both. Let's say if you decide to hide a message within an image, it would be hard to use this. It would be hard for you to identify that message within the image if you use a generic piece of software that is used to render images, for instance, right? Anyway. But the key thing here is extensions. And the message that comes through from the person who's sending you the file, if the data is coming in from the third party, they'll be able to tell you, say, what I'm sending you is an image file, right? I sometimes send through weird, files with weird extensions. Like, for instance, if I asked you what sort of application you think this, actually, what application do you think would be used to open a .sbv file, right? Would you know? Probably not, right? It turns out this is plain text, right? This is how Google Meet exports the chat transcripts that are automatically recorded when we have such interactions. You come across weird extensions like this, for instance. If you don't know, you're at the mercy of the person who is sending you that file, right? So I send you this file, .cls file. I'll need to tell you to say this is maybe a plain text file. A .md file, I'll have to tell you that this is actually plain text, in which case you will know that you just have to use a text editor for you to be able to view the content in this file, right? So you right click and you do an open with, and then you select the appropriate file. You don't do that, you probably get that warning message. I don't know if you can create a warning message where you're told to say, please choose an application to open this file with or something, right? All right, and then so something else you can do is you can if you work with certain types of extensions. We were going to work with some of these extensions, but we probably won't, right? When working with assembler, MIPS assembler here, you can tell your operating system to associate them to a particular application, right? So that by default, when you double click that application, when you double click that file, the data file, a specific application is automatically used to consume or to process the data, right? So in the case of these extensions here, you'd be using QtSpim or something. If you don't do that, I mean, you end up with a situation like this, where you'd think that a particular file maybe is a text file, you open it up and then you see gibberish and you start wondering what is going on. Well, you can't open an MP4 file using a text editor here. You have to use an appropriate file, I suppose. Something else we normally talk about here when we're discussing this notion of how a computer will know how to process the data here is that simply changing the extension, and I think we mentioned this, I hope we did mention this when we were looking at files and file systems. Simply changing an extension doesn't change the data that's encoded within that file, right? So if you have a .mp4 file, right, a video file, and you just change the extension to txt, it will not magically change the contents into text. It doesn't work like that, right? If you are wanting to convert something into a particular file format, a data format, you'd have to explicitly do that using application software. This is the reason why when you're told by your lecturer to say, submit a PDF document, you use application software to export or to re-encode that data into a desired format. In this case, it will be PDF. Simply changing this will not work, right? I come up with this file here, example data. It's an OTD file, simply going to my file system and telling my file system that, and I'm going to copy this across, I guess, so that I have a backup. Simply telling my operating system that I want to change this file extension to PDF will not magically change the way that the data is encoded in this file. You need to use application software, right? So in this case, depending on the sort of word processor you use, you typically have a feature that allows you to export to PDF. So You go through this nice process here. Then you'd have your PDF document converted for you. Do you think is there a way of converting an MP3 file into a Word document? Is it possible, you think?
I don't think so.
I don't know. Maybe not. We don't know. Maybe we should ask this question in the assessment. I'm sure people won't be able to cheat or something. Okay. So the idea, right, is now that we know how data is encoded, and we've had a conversation around this notion that space is a premium, even though secondary storage is increasingly becoming cheap, but because we are continuously generating massive amounts of data, we need to be extremely careful when it comes to how we use the data. For instance, when it comes to video, we need to be very careful what sort of resolution we are working with, right? Because the higher the resolution, the higher the file size. So this leads us to our discussion of so-called data compression, which is nothing more than a technique that allows you to drastically reduce the file size associated with data encoded in an existing file. We've already discussed that data is typically encoded in different formats here. We typically work with different types of data. So we have to be very careful in how we get to encode this data, because ultimately, once we have the data, at some stage we need to archive it to secondary storage. At some stage we might need to think about transmitting it maybe via a network or via the internet, for instance, to send it to somebody else. When we're transmitting data to a third party, we know that that implicitly translates to money, right? And so we have to be very careful how large the payload is that we're sending to the other side. This is where compression comes in. So compression is nothing more than the process of reducing the size of the data that you have encoded. And the idea is you want to be able to efficiently utilize the available space that you have at your disposal, and also to be able to quickly and effectively transmit data across the network. It turns out that there are two main types of data compression. There's so-called lossless compression, where you reduce the size of the data without compromising the quality. And then there's so-called lossy compression, where reducing the size of the data results in a reduction or a compromise on the quality of the data. Right? I don't know if that makes sense. So in both cases, you're reducing the size, but the fundamental difference between lossy and lossless compression is that with lossless compression, the quality of the data remains intact. Effectively, what we're saying is that the bits that you have associated with the data will remain as is. But with lossy compression, part of what you're doing is you're removing some of the bits of the data from the original data, right? And this makes sense for things like video, right? When you're converting, or when you want to change a resolution from 4K to 240p, for instance, you're going to compromise the quality, right? Which is why the video that results is not visually appealing. Right? Is this making sense? Lossy and lossless compression. I'm sure you've used lossless compression numerous times, right? Has anybody ever zipped a file and sent it to somebody else? Yeah, that's a classic example of lossless compression. Because if I have a file, let's say if I have a folder, like I'm just going to copy this here. Just going to compression. And then I'm going to copy across. I want to copy across. I need a good enough example here. I hope it's going to work, but I need a good enough example for this to I need a good enough example for this to work, I think. Just give me a second. Slides are probably going to be large, right? Okay, so we'll work with slides, copy them here. So with lossless compression, classic example you can think of is where you have, let's say, a folder. Like in here, we have a folder called slides, right? If we check the space of slides, you notice that it's quite huge actually. It's about 506 megabytes. But the thing is, let's say I want to send these 506 megabytes to somebody, but I don't want to send them in their original form, like there. I can zip this, right? I can zip this. I can zip this, and then what is going to result is an archived file that hopefully is going to be less than 506 megabytes. So what I would do then is I would send that slightly smaller sized payload containing the original data, the slides, to whoever is interested in consuming this. The advantage with doing that is, if you notice, I now have 438 instead of 506 megabytes, right? A drastic reduction, not so much, but still significant nonetheless, right? I know that I'll be able to pay less money by way of bundles. I know that I'll be able to transmit this resulting size, this resulting file rather, much faster than the 506 megabytes. And it makes sense, right? It ties on to the question that somebody asked not too long ago, where they were trying to find out if the issue of throughput is going to come back. Well, it's coming back right now, right? If you were wanting to send these slides to somebody, one of the ways in which you'd be able to figure out, let's say, how quickly you'd be able to send these two files to a third party or to somebody else is, you look at the size and the throughput that you're working with, and then you'll be able to derive the amount of time it's going to take. But we do know that 434 megabytes is going to take much less time than 506 megabytes. What we have done effectively by compressing this slides folder into a slides.zip file is we have applied lossless compression. When the other person downloads the zip file and compresses the zip file, the data that you'll be able to consume will be in its original form. The quality will be intact, right? Compare and contrast with lossy compression, where I download a 4K video and then I transcode it to, let's say, 720p or maybe to 144p. What's going to happen is the thing that you're going to view cannot be viewed in its original form, right? So you can't upscale a 144p to 4K, for instance. Is this making sense? Right? So it turns out that for you to be able to compress data, right? For you to be able to compress data, whether it's using lossy compression or lossless compression, you need application software. And I just highlighted an example of zip utility that I just used to compress data to effectively apply lossless compression. And so once compressed, obviously, if you have another person that needs to consume that data, they need to have application software to uncompress the data. If you don't have utility software that allows you to uncompress this zip file, you'll not be able to consume this data, right? And zip is just one of those few examples. I could just as well have used gzip here, right? So if I send you, maybe we can actually, right? Let me do this, gzip. Maybe gzip z or something. Ooh, gzip dot, wow. What extract? How do I gzip slides.gz slide? No, slides or slides.gz. Oops, sorry about that. I'm forgetting how this utility gzip. Anyway. Oh, recursive, I guess. Beautiful. So yeah, trial and error always works if you do this. So and I'm using, the reason I've decided to use gzip, which is another utility software tool that you can use to apply lossless compression, right? The reason I'm using this is I'm trying to highlight the fact that if you don't have application software that allows you to, oh, really? Okay, that's fine. If you don't have application software that allows you to, that allows, I think it's tar though, that allows you to compress, yes. Anyway, that's fine. If you don't have the utility software required for you to uncompress a compressed file that has been sent to you, you'll be dead in the water, right? Because there's no way of consuming that data. So you'd have to download an application software, appropriate application software, and then you uncompress the file. And I know you've gone through this process where you start looking up online, right? How do you use .gz file? How do you open a .gz file? What software to open .gz file? All right, so if you're on Linux, so you just use Gunzip or something. Again, your file extension will implicitly help you identify or figure out what sort of utility software you need to use to uncompress that file. Is this making sense?
I
Yes,
have a
sir.
question.
Yes. Yes, please.
Okay. I don't know if Linux works the same way as Windows. There was an instance where I downloaded a file which was compressed using WinRAR, and so
Okay.
the file extension was RAR.
Yeah.
And then I just changed the file extension to zip, and then I was able to open the same file using File Explorer on Windows. I don't know if it's the same with Linux.
No. So you see, the great question, by the way. The reason, right, is for most of these, here's the thing. Which version of Windows were you using?
It was Windows 10.
Okay. Here's the thing, right? Have you ever found yourself in a situation where you're using Ubuntu, right? LibreOffice, but you're able to open a document created using Microsoft Word? Have you done that before? Anybody in here? Anyone? Standards. That's what I'm trying to get at. Most of these application softwares, irrespective of the fact that there's a different variation, but it turns out that the way they're implemented takes into account existing standards. So if you implement something that is based on some pre-existing standard, then it doesn't matter which sort of application software you're going to use, right? So probably, I'm just speculating here, the reason why you were able to use the Windows utility to open that archive is because obviously archive is standardized. Now, I don't know what sort of standard or what sort of compression algorithm is used by WinRAR, whether it's the same as WinZip, whether they are similar. If they are similar, then that's a likely explanation as to why that was possible. When you send me a Word document, and I'm trying to see, yeah, it doesn't. When you send me a Word document, I'm trying to think of a good example here. In fact, if I was to send you an OTD file, right? An OTD file, I'm pretty sure you'll be able to open this in Microsoft Word without, you can just change the extension actually and just be able to open it up. I've done this myself. Somebody sends me a .docx, although sometimes you run into trouble, you just change it to maybe .doc or something. You should be able to open it using LibreOffice or something. So the reason, Philip, is likely because the standards that is used to implement WinRAR as an application is pretty much the same as, or is taken into account by the default application that you are using in Windows. I don't know, what application did you say you're using in Windows? Is there a built-in utility tool or something?
No, I just use the File Explorer.
Yeah. Well, I mean, I'm sure the File Explorer has a feature that recognizes the fact that allows you to open a popular file format like a compressed file. Everybody compresses file these days, right? Or at least people used to way back. It's not as common these days as it used to be. Why? Because why do you think compressing files is not as common? How many of you have compressed files before? Has anybody ever used WinZip here? Or WinRAR? Besides Philip, has anybody else ever heard of WinRAR?
We've used doing WinRAR, sir.
Okay. Yeah. Yeah, before we part ways here, can you just type 1 if you've used either WinRAR or WinZip, and then type 0 if you haven't? I'm just interested in the chat. I'm trying to get at something here, right? You have to think here. Back in the day, you can type 1 or 0 or something. Back in the day, right? These were crucial applications. And in fact, it was hard to get a hold of a tool like WinZip. You'd have to either use a cracked, and there we go, Tapio hasn't used it yet. You'd have to get a cracked version for you to be able to use it, right? Or you get an evaluation copy or something. But these days, it's not as important. Why do you think that's the case? Why do you think that we have people like Tapio that don't really care so much about WinZip or zip files or WinRAR? Why do you think that's the case?
Personally, I think that the files or encoding being used now is able to reduce the sizes of the same files. So in terms of compression, there's not really that much need.
Not quite. Not quite, Philip. I'll give you an example of what I just did right now. When I compress this folder, see the folder itself, the slides folder has 506 megabytes, right? It's 506 megabytes in size. The compressed version is 438 megabytes in size. I mean, so the key thing here is, if you think about it, if you ask Tapio how much, what size is her SD card on her phone, she probably has maybe 64 GB, right? She doesn't care. She doesn't care that she can, if I send her these slides here, she does not care that she's able to conserve or she's able to reclaim this much space. It's inconsequential. Why? Because space has become cheap. She doesn't mind that she's occupying, or she wouldn't mind that she'll be occupying an extra 68 megabytes of space. It's nothing compared to the amount of space she has access to. She doesn't care. She wouldn't care that she'd be sending 506 megabytes over the network as opposed to 438. Why? Because data has become cheap. That was not the case many, many years ago. Guys, I'm going to ask that we, maybe we can finish, I guess. I don't know. Yeah, I guess we're almost done here. I was going to say we part ways or something, but anyway, so I guess this was just an example here where we were compressing, we were trying to compress the size here, similar to what I just did here. So you have a directory which occupies 419 megabytes, and then once compressed, you notice that you drastically reduce the payload, right, by about 13%. Now, now, even though a person like Tapio might not really care so much about these micro differences, but if you think about it from a perspective of a situation where maybe you are generating data on a daily basis, a compression or a gain of 13% would be really significant, because in a month's time, this 13% will result in something much, much larger, right? Sorry, let me just, hi, can I call you back in class? Thanks. Yeah, so don't know who that was, but don't know. All right. Yeah, that was disturbing. Normally I don't normally pick up, but I just thought maybe it was important, probably not important anyway. Now, the other thing to think about compression here is that is that some tools, right? Some tools will result in significantly smaller files because of the algorithm that is used, obviously. So if you're obsessing a lot about making sure that you compress the files to as low a file size as possible, then you'd have to pay particular attention to the type of file that you use. I love tools like gzip, for instance. It really dumbs down the, I wish I could showcase the comparison of, yeah, I wish I had this thing. Maybe I do. Maybe I can showcase the comparison of, yeah, maybe I should. I don't know if I would be able to. The comparison of WinZip and gzip. I'll use the same file. I think this would be good enough. India PD. Is this making sense or not?
Yes, sir.
Yeah, you probably haven't yet gotten to a stage where you really value some of these things that I'm talking about. But I find myself in instances. I just remembered something here. If you look at this screen grab here, I've been working with large text files, huge text files, right? So this example payload here, for instance, this batch here is 161 megabytes, and I have I probably have, I guess, probably almost I would say maybe a little over 5,000 of these or something. So as I'm working with these files, I move them back and forth to my local computer, the computer I'm working on, and then back to the server once I process them. And so compression becomes really handy, right? I'm just going to see if I can locate this file. No, I can't find it. That's fine. I would have really loved to showcase the differences in the differences in the gain that you get, right, when you use gzip and when you use zip, for instance. All right, I don't know who has the microphone on, but there's a little bit of echo there. Right, so it turns out that you find these things here. And by the way, most of what we've been talking about here when I'm talking about compressing folders and compressing things like text files, that's lossless compression, right? Lossy compression is typically associated with things like video, sound, images, right? And you've seen this implicitly in Word documents. I don't know if you've used this feature before, but your typical Word application, Word processor will allow you to compress the resulting document, right? So if you end up with a Word document that's maybe 20 megabytes in size, and maybe your lecturer tells you to say, make sure that the file that you're sending to Moodle, or in fact, you realize that Moodle has a limit when you're uploading files. What you can do is you can apply lossy compression. You do this implicitly, and with tools like LibreOffice, for instance, or OpenOffice, all you have to do is just specify the number of dots per inch associated with the different images you have in the Word document, right? In certain instances, it can be as easy as you just choosing this feature here to say, for all images, apply lossless compression, and alter the compression in such a way that you just maintain 90% of the quality. Right, I'm going to showcase an example before part ways, right? I think it would be nice if I showcase an example. Observe, if I have this document, right, and I decide to say I'm going to, oh my goodness, I'm going to use, I hope I have a large file. I hope I do have a large file here. Probably not. Wow, these are not. I was kind of hoping I would have a relatively large file. I was really hoping I would have a huge file, actually, a huge image file, because this works better when you have let's try and see here the PNG. In reverse. Beautiful. So if you look at, oh, I don't want to use the Mr. Moya's. If you look at this, oops, sorry. If you look at if you look at this file here, this image, this PNG file, it has 1.2 megabytes in size, right? I'll open it using GwenView. Right, beautiful. It's 1.2 megabytes in size, but If I import it in a Word document, right? If I say I want to insert this as an image in a Word document like this, I want to embed it in here. I'm going to go to its location, which is downloads, and then just insert it here, right? If I save this file, what you immediately notice is that if I check the file size here, come on, if I check the file size here, you notice it's 1.1 megabytes in size, right? If I'm not happy with this file size, I can tell when I'm exporting this, let's say to PDF, I can tell my PDF exporter to say apply lossy compression, or I can tell it apply lossless compression, maintain the size. What I'm going to do is I'm going to maintain the size first, right? Export it, and then I'll say original size. And then I'm going to export it again. And then I'm going to apply lossy compression so that you see the differences inside. So I'll apply JPEG compression, and I'll say, I want the quality, and we'll do something drastic here. 10%. Export this, and then I'll call this lossy compression. So what has happened, maybe it's not very visible here, probably a bad example here, but if I go back to my thing here and check the sizes, have you noticed that the one with lossy compression has 1.3 megabytes, and then the one with lossless compression has 1.9 megabytes. The idea here is the resulting file, the only thing that is being compressed here is the image. You can't compress text, right? Can you? Can you apply lossy compression to text? No, you'd lose the meaning. Right?
No.
Yeah, and I guess you can also see the differences in the images here. Just small little difference here. I don't know if you can see this. Yeah, just small little difference. If you see the green here, I don't know. Right, so this is everywhere, right? You find this in these funny tools that you use, like Photoshop, for instance. You find them everywhere, right? This is not really part of the syllabus. Was going to talk about the Huffman coding, which is nothing more than an algorithm that is used to apply compression, right? Just to illustrate how compression works, but it's not really important. If you're feeling adventurous, I do encourage you to go look it up. I guess it will help you understand how things are done internally. Guys, I guess lecture series number 15 is a wrap. When we meet next, we will start looking at a very watered down version of the topics we're supposed to cover. Now, I've heard in the grapevine that it's likely that the semester might be apparently extended. If that's the case, then we will do these things, which would be good, actually. All right. Was there a question? Sorry.
So,
Yes.
I don't know if you addressed this in the last lecture series, but I sent an email in regards to regrading. I don't know if it will be considered.
What regrading is this?
For lecture series, for quiz number 15, I wrote bits. I included bits in my answers.
Oh yeah, that will be regraded. I'm sorry. I haven't responded because I'm only going to respond. You're not the only one, actually. There are a few other people. I'll only respond once the regrading has been done. That will be fixed. That will be fixed. And I know there are a few other people that requested for a regrading. I don't know if that was resolved for quiz number 14 or something. That will be addressed. Is that fine?
Thank you.
All right, good.
Yes,
I'll see you when you. Yeah, thanks, Mr. Pio. I'll see you when you see me. I don't know if we're going to have class tomorrow. Maybe tomorrow. I think what I'm thinking of doing is maybe we can use tomorrow to. I think we should have class and just have. It's going to be one of those short classes where it's just an overview of what to expect in the test. If not, then we'll do that on Monday, since the test is on Friday. All right. If I'm unable to make it on Sunday, I shall send out communication. Thanks. Please stay safe, and let's pray. Not praying for speed. I pray for speed myself sometimes, but let's pray that the semester is slightly extended so that we cover the remaining interesting portions. There's some interesting stuff that's remaining. All right. See you. Thanks. Stay safe.
Right, sir.